So when can we say two events are independent events? That's the question we'll try to answer in this video. Let's take the first example. Let's look at the student population of Mercy College, 20% men, 80% women. So if I randomly select a student from Mercy College, then the probability that the student is male is 0.20, and the probability that the student is female is 0.80. So if I say yesterday I met a person, and my question is, what is the probability that the person is female? So I just said I met some random person, and I need to know the probability that the person is female. Then you're probably thinking that 50% of the general population is male and 50% of the population is female. So the probability that the person I met yesterday is female is 50%, which is 0.50, and you're absolutely correct. But now I'm going to give you a clue, and my clue is this. The person I met yesterday is a student in Mercy College. And now I'm going to ask you the same question. What is the probability that the person I met yesterday is female? But remember that now you know that the student is from, or the person is a student in Mercy College. So now you have to rethink this probability. This answer is not going to work anymore now that you know that the person I met yesterday is a student in Mercy College. So now you're going to say, since the person I met yesterday is a student at Mercy College, the probability that the person is female is 80%. And that's because 80% of the population, student population in Mercy College is female. So we changed our answer from 0.50 to 0.80. Now let's look at the two events. One is being female or being a woman. So let's call that F. And the other event is being a student in Mercy College. So that's our second event. So being a student, let's say, at Mercy, and this is being female. So are the two events, being female and being a student at Mercy College, independent events? So let's examine the probabilities. In general, the probability that the person I met yesterday is female is 50% or 0.50. But knowing that the person I met yesterday is a student from Mercy College changed the probability that the person is female. So the minute I said, or you found out that this person I met yesterday is a student from Mercy College, you changed your probability point from 0.50 to 0.80. So being from a student from Mercy College affects the probability that the person is female. Now that's telling us that the two events, being female and being a student of Mercy College, are not independent of each other, because being from Mercy College affects the probability that the person is female. So the two events not independent. Now let's look at the next example. The color of the person's eyes being blue, so that's one event, and the person's IQ being 140, are the two events independent? That is, if you know that the person's eyes are blue, is that going to change the probability that the person's IQ is 140? And I'm sure all of you will agree that a person's IQ has nothing to do with the color of the person's eyes. So knowing that the person's eyes are blue are not going to change the probability that the person's IQ is 140. So the two events are independent. So that's an example of a pair of events that are independent. So let's look at question 1. Suppose we're tossing a coin continuously and we get heads the first 100 tosses. It's rare, but it could happen. Now knowing that, so you know that the first 100 tosses of a fair coin, and it's important to know that it's a fair coin, were heads. Now what is the probability that we toss the coin again and the 101st toss is again heads? So the answer to that question is 0.5. It's still 50-50. So knowing that the previous 100 tosses were heads does not change the probability that the next toss will again be heads, because each toss, what happens in each toss is independent of what happens in the next toss. So they're independent events. So this is another example of independent events. Now let's look at question 2. Gender of the first child is female and the gender of the second child is male. So are the two events independent or are they not independent? Now if you know that the first child is female, is that going to affect the probability that the second child is male? And the answer is no. The fact that the first child is female does not change the probability that the second child being male is still 50%. So the two events are independent. Now let's look at this example where there's an artificial pond with 10 male frogs and 10 female frogs. So there's a total of 20 frogs, 10 male and 10 female. What is the probability of capturing a male frog? And if it's completely random, then it would just be 10 male out of 20 total, so that's 10 out of 20, that's 0.5 or 50%. So if the first frog is male and then you go back and pick another male frog, what is the probability that in your second capture you get a male frog again? So now if you think about it, you'll have to consider what happened in the previous pick. In the previous pick we got a male frog, which means now in the artificial pond we have just 9 male frogs because one has been captured out of now we have 1 frog less, which means we have 19 frogs. So the probability of the second capture being male is 9 out of 19. Now here, when we were considering the calculations for selecting a male frog in the second capture, we did have to consider what happened before, which means the two events are not independent. Now in part C, what if we were sampling from a huge population, hundreds of thousands of frogs? Let's say our first pick is a male frog. What is the probability that the second pick is a male frog again? Now, do you need to consider what happened in the first pick when the population is this large? The answer is no. If the populations are large, then what happens in the first pick does not affect the probability of what happens in the second pick because of the very large numbers. So that is in the case of hundreds and thousands or hundreds of thousands of frogs, large populations.